Let's go through the unconfined case for the equilibrium well equations. We'll go through the non-equilibrium or transient in a little bit, but the equilibrium kind of helps us to understand the ideas of drawdown and how it works. So we have an unconfined aquifer, and we have a water table. I'll draw that like that. The water level is there. And then we start pumping it at a pumping rate of Q again, and we pump it for a long, long time till it gets to the equilibrium. And it draws down. So we'll do again, it draws down. Let's say it goes to about there. And then we have this drawdown curve around there, like we showed in the confined case. And maybe I'll kind of do like that. That's not very symmetrical, but it should be symmetrical. It's radial. And so we have the drawdown and the heads. I've already given away the punchline that for the unconfined case, the actual head, it matters, not just the drawdown. So we have H1, and then we have the drawdown, which again is the initial head minus the head after pumping. We call that an est. 0 minus H, that's an equal sign there. And again, we have the initial head is before we pump it, and we can have the heads at a couple different radii. So I'll call this one H2. And those are at I'll call the closest one, radius 1, just like in the unconfined case. It doesn't really matter how you order them. The signs will work out if you keep track of the heads and with the right head with the right radius. And then we have RW at the well. Somewhere out there, we get to a place where there's no drawdown. We call that the radius of influence. And mathematically, that never quite happens, but I'll mention it briefly, of influence. You can't read that, but there's a radius of influence out there somewhere, and that's where the well has no influence, so there's no drawdown. Darcy's law, again in radial coordinates, says that the flow equals Ka, we don't have that minus sign now, change in head with radial distance. Now the area of flow for the unconfined case, the water is actually at this level here, H, at some distance there. So remember, in the confined case, the area of flow was the aquifer thickness times 2 pi r. In this case, the area of flow is going to be 2 pi r times h, where h is a variable, is a function of r. So I rearrange this or plug this in. I get the flow equals 2 pi r k h, that's a k, dh dr. If I integrate that thing, I end up I'll put my r's on the left side, so I have 1 over r dr equals 2 pi over k over q, 2 pi times k over q times h dh. And if I integrate h dh, I get an h squared over 2. Rearranging, I get q equals pi k h2 squared minus h1 squared over the log of r2 over r1. And I rearrange that to solve for q. I get k equals q over pi times h2 squared minus h1 squared on the bottom there. Extend that out there. Times the log of r2 over r1. So that's with it arranged to solve for k, given the heads of the different radii and the flow direction. Notice that the h2 squared minus h1 squared is not equal to, and this is just the note says here, s2 squared minus s1 squared. So that's why we can't just use the drawdowns. We need the actual heads. So here's the summary of the two equations. The square tells you that this one is for the unconfined case, and the non-square tells that this one is for the confined case. Also, the fact that it uses a T instead of a K, or T equals KB, tells you that it's confined. All right, so here's an example of the unconfined case. Water table aquifer, that means it's unconfined. Water table aquifer, unconfined mean the same thing. Pumping at 100 gallons per minute from a 4-inch diameter well, that means the pipe is 4-inch diameters, in a 6-inch diameter borehole. So the radius of the well then is going to be 3 inches or 0.25 feet. So you drill the hole and then you put the pipe in there, and then around the screen interval, you have gravel or some really permeable stuff right around there. So really the hole, as far as determining the hydraulic conductivity, the hole is 0.25 feet, and then you have in radius, so you have the natural material outside of that. All right, so we have these numbers here. The initial head is 110 feet. The head is 96 feet at a radius of 50 and 88 feet at a radius of 20. From this equation up here, on the previous page, I have it arranged for K. K equals Q over pi times H2 squared minus H1 squared times the natural log of R2 over R1. And like I keep saying, it doesn't really matter which one you call 1 and which one you call 2, as long as you line up H2 here with R2 there. Notice also in the equation, confined case has a 2 in it. The unconfined case does not have a 2 in there. All right, so I'll plug my numbers in here, and we get Q is 100 gallons per minute. Do a unit conversion on there. H2, maybe I'll call this 1 and this one 2. So I have, well, I might as well write it out. 100 gallons per minute over pi times H2 is 96 feet squared, minus H1 is 88 feet. Square that, times the natural log of R2 is 50, R1 is 20. And I have this written down here. If you convert this Q in gallons per minute to feet cubed per day, go through that conversion, you get 3.8 feet per day is the hydraulic conductivity. What is the drawdown at the pumping well? Well, how about if we go back to this equation here, H2 squared minus H1 squared, maybe we'll call the pumping well H2. So H, part B, H well squared equals H1 squared plus Q over pi K times the log of 0.25 feet, that's RW, over 20 feet is R1. And that goes to, unsquare H well equals 26 feet, if I did that right. So we get H well squared, and then we unsquare that. I think it comes up to 25 feet, so the 26 feet. So the drawdown equals 110 feet initial head minus the 26 feet final head equals 84 feet. So it's 84 feet at a radius of the well. The radius of 20 feet, it's 110 minus 88 is 22 feet drawdown. At a radius of 50 feet, it's 110 minus 96, drawdown of 14 feet. So part C, what is the radius of influence? Okay, this is not really how you find a radius of influence. The way we do it is you plot the drawdown versus distance, and you kind of do it on a semi-log scale and then extend it up to 0. But here's a way to do it. So what I'm going to do is I'm going to set the H equals H0 equals 110 feet at the radius of influence. I'll call it ROI. So if I solve for that equation, so I solve this equation right here for R2, so I can have R1 be one of these 2 points, and then R2 be the radius of influence, and then I solve for the radius of influence, setting the head equal to 1 10 feet and using one of those other points. I don't know if you followed all that. You get the radius of influence equals 300 feet. So this is manipulating this equation, but I wanted to give you a good feel for how the drawdown works, how the drawdown curve works, the curvature to that, and what we mean by drawdown and head in the confined and the unconfined case. So the next video, I'll walk you through a homework on this.